Hello, my name is Edmund Burke, the CEO of Space Information Laboratories. We're an innovation leader in lithium-ion intelligent batteries and consolidated avionics. SIL's primary business is we work space R&D for DoD and NASA and aerospace companies as a supplier. We're a full AS9100D quality management system company, DCA approved accounting, DCMA approved inventory system. We do master inspection points on our technology. We're located in Santa Maria, California, right near Vandenberg Air Force Base, which is space and missile country in California, Central Coast. Some of our customers we go directly to Air Force, Missile Defense Agency, NavAir, and we also have contracts directly as a supplier to Lockheed Martin, MIT Lincoln Labs, NanoRacks, and some of the next gen or new space companies, Firefly, Generation Orbit. We have a full in-house space qual environmental capability, so we have our own thermal vac chamber, random and sign vibe machine, shock machine, thermal chambers, so we can ATP our own flight units for rapid delivery. Today's presentation is going to be about our lithium-ion polymer Intelli-Pack, FTS avionics and telemetry battery technology. We're pioneering new intelligent batteries for safety critical applications on missiles, rockets, satellites, or aircraft. Current product line across the board, we go from small batteries, from 2 amp hour up to 200 amp hour in size. They all have an intelligent battery management system within the battery that protects, balances, and monitors every cell and outputs telemetry data that can come down from these vehicles, aerospace vehicles. And we'll talk more about that today, the intelligence and the safety aspects of this lithium-ion battery technology. The cells we're using are lithium-ion polymer Z-fold pouch cells where you have stacked anode and cathode plates that are Z-folded together with polymer material in between the cells. There is electrolyte, but it's gelled, and there's no real leakage of electrolyte that can just spill out of these cells, even if you poke a hole in the cell. They're being used in mass scale production for many electric vehicle applications. Chevy Bolt actually uses this technology in electric vehicles. They're also used in your cell phones, and so the real benefit of this technology is it's very low internal resistance. They're stacked plates, unlike a Jelly Roll 18650 where you have a big long anode plate and cathode that's rolled. This internal impedance is like a tenth less in resistance. So what you get is very rapid rechargeability. You get high current discharge capability. The chemistry depends. There's various chemistries you can get with this, NMZ, LCO, or you could even get iron phosphate in a pouch Z-fold cell like this. So if you need an application where you have higher cycle life, like a satellite, we usually use NMZ, which is very high energy density, and it's got excellent cycle life. This shows a little bit more about the cell, and you can see in the picture on the left the description of the Z-folded stacked parallel cathode and anode plates that I described. This is some testing that we've done where we did NAV CS 9310 testing. You can see the cell on the right we put between plates. We heated it up and see where it went into thermal runaway. They did extremely well. Literature says 120 C, but we hot plated it to 170 and then it went into thermal runaway, where the fire would come out near the tab side. You can see here on the right the picture of the fire coming out. We also did gross overcharge, where we took the cell. Normally, you do not want to charge it more than like 4.25 volts. 4.2 volts is fully charged. We charge it to 5.3 volts at 1C charge rate, which is, this cell is 10 amps, 10 amp hour cell, so 1C charge rate is 10 amps. There was 30 amp hour added capacity. There was no fire at that level. 5.3 volts, 1C charge rate, no fire came out. We had to push the cell to 5.3 volts at 2C charge rate to get it to go into thermal runaway. Took about 30 minutes, added 30 more amp hour above the 10 amp hour capacity that's required. So it's a gross overcharge to get this into a thermal runaway event, this NAVC testing shows. We also did a pinch test, 1,500 pounds, where we had a ball, two balls, and pressed them as hard as we could together. The cell really didn't care. There was really no change in open circuit voltage or temperature, and slight difference in capacity over 107 charge and discharge cycles. Also did a broad face indent test where we used a metal and ceramic tip, and we tried to induce a thermal runaway event. Internal short circuit happened at 57.6 pounds, so we had to really poke pretty deep into this cell to short the plates. So it's pretty robust, and we induced a thermal runaway event with metal and ceramic tip we were working with. Can we just go right through the cell with a ceramic tip? And I think we can do that, but it does still short plates when you crush, crush indent through. So we did it on the top and also the side. So the top, you had 57.6 pounds of force to get into thermal runaway, and then on the narrow side of the cell, you see here, we induced 37 pounds and induced a thermal runaway event. And this testing worked closely with Aerospace Corporation in LA, the energy lab there, and enjoyed working with those guys for this DoD program. This is a 20 amp hour battery that we went through 3 actually range safety qual programs successfully, 13 for 13 mission success, and this battery weighs 14.5 pounds. We actually replaced a battery, a NiCad battery that weighed 65 pounds, and we saved over 150 pounds on just by a battery replacement on the DoD program. This shows a test that we did, a shock test that we basically took the battery. This is a couple thousand G shock on an Avco, where you raise it up and then you just slam it in 3 axes. You do plus or minus, so 18 times 3 axis, and you'll see a big shock event. Look at the machine shake. And our battery technology and our patents has how we package these lithium polymer pouch cells so that it doesn't extreme shock and vibe and thermal cyclone vacuum. They work perfectly. Here's the shock qualification, range safety space qualification levels. We've done this 3 different times in different environments, 2013, 15, and 17 for different customers. We did a thermal cycle, -10 to +55C, and these are 319 and 324.01 range safety tests, where you do 24 cycles, 2-hour dwells. And then the thermal vacuum, we did 1 × 10 to -5, 4 cycles on that. And then random vibe at 16.4 GRMS, 3 minutes per axis. We actually confidence tested it at twice this level, all the levels you see here. The random vibe, we did 32.8, and then confidence in the battery passed. Sine vibe, you can see the levels. Shock at 100 hertz, 222 G, and 1800 hertz at 735 G. We actually confidence tested at 2 times this level. So extreme shock and vibe, no problem. And then we also ran all the mil standard 461 EMI EMC tests on the battery, and they all and the battery passed. So the guidelines for range safety, environmental qualifications, and also designing a lithium-ion battery for launch vehicle applications is in these documents. NAVC, we do NAVC testing on the batteries, and that's really cell and destructive ladder battery testing. These cells have done extremely well in batteries and through this testing. There's no pass-fail here. They're just trying to see the safety aspect, how safe the battery cells are, and how safe the battery design is, and on, if it catches on fire, and then how can it be stifled or so. There's also SMC has design guides for lithium-ion batteries, SMC 018, and also the test guideline SMC 016 that we follow. Also, our batteries for our FTS batteries, RCC 319, we follow that for all the cell screening and environmental qual testing. It defines what tests we have to do in the cell testing. So our batteries are compliant to that. And also 32401, if you're doing an avionics or telemetry battery, then you have to follow 32401, and it references back 319 for all the cell screening and testing. So there's no real much difference in the cell screening and testing between telemetry avionics battery and FTS battery. We also have designed our BMS to pass all the UN 38.3 tests for shipping, tests 1 through 5 and 7. Which has to do with they put you through short circuit test and over voltage where a battery automatically shut off. So we've designed a BMS that's internal to our battery to pass all those tests. Next slide. Overall, our battery design, we call it PPE, which is we protect, prevent, and enclose. That's our prevent, protect, prevent, and enclose technologies to stop cell failure propagation, limit cell-to-cell thermal transport, and safely contain flames and debris in the battery. So our approach, we protect with our BMS. We have a most advanced BMS in our battery. It has real-time monitoring of all cells and cell balancing capability to ensure safety. It protects the cells against overvoltage, undervoltage, overcurrent, short circuit, and thermal protections all built in. Our BMS is totally agnostic to cell chemistry, so we actually can work with any lithium ion chemistry or actually other chemistries outside of lithium ion. And we have total settings that we have in firmware that we put into the battery for totally agnostic. We also can detect temperature sensors and hotspots on the cell, and we have customizable, programmable, designed to trigger prior to hazard situations capability in our BMS. We also have been working with some customers with thermal phase change material to isolate each cell pair, each cell in the battery. So if one run into thermal runaway, the heat from it would not make it to the next cell that's on top of it. So been working with that for several military customers. We actually just won a contract where we're actually going to make a battery where it could take bullet fire and not catch on fire. So we're pushing the envelope with that. We also, our battery enclosure is designed to, it's milled aluminum. It's designed to handle, contain the energy, and it's packed. We have special fire rated foam, 94 VO1 inside the enclosure. We try to not have very little airs left in the enclosure itself. The housing can withstand a cell failure without flame or debris expulsion. We also can built in a vent to customers' requirement to where they need the vent to be. We've tested this enclosure and total battery and extreme shock, vibe, thermal cycle, and vacuum acceleration, ESD and EMI&C environments, and have done very well through all the range safety space qualification programs. Every SIL battery has an advanced BMS within the battery. It has ability to output 1 Hertz data, all your battery voltage, current, cell voltages. We have a state of charge and state of health algorithm that we run in the battery. We have protection features where we have charge, discharge, and temperature protection. We have autonomous built-in tests, min-max data recorder that saves your min-max values just in case the technician has an issue, or like a power supply went off and failed, and it's failed, we can record a lot of those min-max values. We also have a standby mode, and very low. We basically go in sleep mode, draw less than 20 microamps in sleep mode. The BMS is totally agnostic to cell chemistry. It has automatic cell balancing. It has automatic heater control from 0 to -55, totally selectable. We have a GUI, Windows GUI and data logger that we provide with all our batteries. And you can see here all the cell voltages are on the left. You have a status of the cell balancing capability. We also monitor the telemetry message received. We tell if you're charging or discharging, the current magnitude indicator. We tell you the state of charge of the battery. Algorithm runs. We have a heater, which tells you if your heater's on and off, and then all your critical bits for your charge FET and discharge FET. We show you if the charge FET opens up or the discharge FET opens up, or if you have an over voltage or under voltage protection, which will show you if that happens in real time. The user is the last defense for safety. When we give them the total capability to see every aspect of this battery during charge and discharge. Also, we record all the voltages, all this in CSV files, so you can do all your plotting after your charge and discharge operations with this battery. So it's an incredibly turnkey system that allows instant insight into the battery. No battery chargers required. A commercial off-the-shelf power supply and load that you already own can be used with our battery. This is a 5 amp hour battery, FTS telemetry battery. The spec sheets on it, you see here, very low swap. It can produce 100 amps pulse current or 30 amps continuous current. Space call range -10 to +55 with heaters, and without heaters, excuse me, and with heaters -40 to +55. Temperature range. This battery has very low internal resistance. I've been talking about that earlier on. You can see at a 240 amp pulse, the battery discharge goes from 31.56 to 24.16, so only about a 7.4 volt difference at a 240 amp pulse. If you tried that with an 18650 cell, it would basically drop the voltage down to, probably like 10 volts or less, because the internal resistance of those cells are 60 milliohm versus like 5 milliohm, 1/10 of it for this cell. This shows did a test, very fast charge capability from a 0 stated charge to 100%. A 2C charge rate, which is 10 amps on a 5 amp hour cell. It recharges in less than 30 minutes, and from 50% stated charge to full charge is less than 16 minutes. So that's a game changer for rapid charge capability on a satellite or a launch vehicle, or if you want to use it where you're just putting the battery at 50% or 35% stated charge on an aircraft, and you want to fully charge by the time you drop the weapon, you could do that and replace thermal batteries. We ran it in a vacuum for a year. I tied up a vacuum chamber for a year, and we did a LEO mission at 30% depth of discharge at half a C for charge and discharge, and we measured the internal resistance over the year-long test, which is around 6,200 so cycles. We showed every 100 cycle we did a complete discharge and measured the capacity also. The cell performed flawlessly, and we did 2 cells in the vacuum and 2 cells outside the vacuum, and there was very little difference between the two. And then we measured the capacity and internal resistance as you have more cycles, the internal resistance grows. So you can see this cell started around 3 milliohm and it grew to around 4 milliohm after 6,200 cycles. So this cell is an NMZ cell. It's excellent cycle life compared to an LCO, like 3 times the cycle life of an 18650 LCO. So it's a game changer because it's high energy density, plus it has excellent cycle life and rapid rechargeability. You could basically go from 50% state of charge to full charge on every orbit if you gave it a 1C charge rate. Next slide, we projected the cycle life. This is the plotted cycle life of the cell. You can see after a year, it discharged maybe to not even 94% stated capacity, 94% of its capacity still there. So we projected like how many cycles could we get to 80% capacity, and that's about 22,000 cycles, and that's very conservative. Because we did discharges every 100 cycle, complete discharge of the cells every 100 cycles. So they could easily do 25,000 cycles to 80% capacity, and then to 60% capacity, probably like 50,000 cycles. So excellent for nano, micro, small sat application, our battery technology. The beauty of it, it can power all the spacecraft and also can power high power payloads right from the same battery, which is a game changer. Here's a 3.3 amp hour FTS battery that we have developed that's now in production. Very low swap capability too. It's only 3.25 pounds, 6.7 by 4 by 2.8. This one is 6.6 amp hour capability for continuous and pulse current is 16.5 amp hours. Same type of operational range, minus 10 to plus 60 and minus 40 to plus 71 with heaters inside. Here's another one of our 2.2 amp hour FTS batteries, a very reduced swap. This one can do 30 amps from a 2 amp hour battery. The cells are rated 15C and 60 amp pulse current. We have a program that's using this that needed 20 amps of continuous current on a DoD program of national significance. We'll fly this coming year. And once again, same space qual temperature ranges that I've mentioned. I showed here in this slide, we decided to run a 20 amp pulse, FTS pulse, which is 2 times more than any other FTS pulse. We showed that over the whole 140 minutes with a 20 amp FTS pulse, which is twice the magnitude of any FTS pulse there is in the real world, we still stayed above the 24.5 volt line after a 140 minute discharge. So that's a range safety requirement, and we basically exceeded that with a 20 amp pulse. So the battery really can discharge high current or high pulse current because of the low internal resistance again. This shows the tests we did on the 2 amp hour, the qual tests we did on the 2 amp hour and 5 amp hour batteries. We ran a thermal cycle, RCC 319, 24 cycles, 2 hour dwells, minus 40 and plus 55. We burned in the printed circuit boards before going into the battery, and then did full functional checks at plus 71. The battery BMS operates prior. We did battery level tests, also 24 cycles, 2 hour dwells at minus 40 and plus 55, and this met RCC requirements, and vacuum testing at 1 times 10 and minus 5 torr. Operational shock we did, and also operational random vibe at 16.4 GRMS, and then operational sine vibe plots you see here. Battery works extremely well in extreme shock and vibration levels. We actually in shock, we've tested up in the 2,000 to 3,000 G shock levels. This is another battery we're actually doing for nanoracks, a game changer, 52 amp hour. It will power a metal cutting tool. It's going to cut a slice in the SpaceX booster second stage to show that you can modify a second stage and have an outpost using second stages that are spent stages. This battery only weighs 23 pounds. It's a 52 amp hour battery, very similar design. It has advanced BMS inside. It can do 104 amps. Our BMS can control external MOSFET and sense resistor in this application, and that's all built in. And then this battery then connects to a power distribution unit. We had the metal cutting tool needed 180 volts. So we have a DC-DC converter that can do 1800 watts. That DC converter could also do 120 volts. And then we also had in there plus 3.3, 12, and 28 that powers all the spacecraft subsystems as part of this system, the battery and PDU. So and here's the reduced swap, 23 pounds, 52 amp hour. This is the lightest battery ever produced with advanced BMS all built into the battery. And same type of qualification ranges, minus 40 to plus 60. It outputs all the telemetry as you fly downlink. That's pretty much it. If you have any questions on the slide set, please contact myself, Edmund Burke, or my BD director, Don Culp at Space Information Labs. You have the contact information here. Please feel free to reach out anytime. We can rapidly provide quotes or any other technical input that you need to provide these batteries for your launch vehicles or missiles, small nano micro satellites. Appreciate your time. Thank you.